Rick and Morty play a game where they flip 20 and 21 coins respectively. What is the probability that Rick gets more heads? Give this question 3 minutes and I'll see you back here with a couple of solutions. Before we get to solving this, I would like to send a huge thank you to the channel's first Patreon supporter. Now, let's get to the problem. As with most interview problems, we can assume that the numbers 20 and 21 are arbitrary. To better understand the question, we can look at some other examples. Let's start with a simpler case where the players flip 1 and 2 coins respectively. Rick can either have 0 or 1 heads, while Morty can have between 0 and 2, with 1 being the most likely. Given the potential outcomes of the tosses, there are 8 possible combinations. Only one of them has Rick with more heads than Morty, hence a probability of 1/8. If we loosen the inequality and look for the probability that Rick has at least as many heads as Morty, we have a chance of 50%. Then, we add 1 coin each, getting to 2 and 3 flips. We lay out the possible combinations as before. Count the pairs in which Rick has more heads than Morty, and get that there are 6 out of 32 such cases, which gives a probability of 3 divided by 16. If we look at the cases where Rick has more or as many heads as Morty, we see that it is again equal to 1/2. With this observation in mind, we can proceed to prove that it holds true for any consecutive pair of tosses. Then, we can deduce the probability of strictly more heads. To put this into formula, let x of n be the number of heads Rick has from n tosses, and y of n be the number of heads Morty has from n plus 1 tosses. We know that for n equal to 1 and 2, the probability that x of n is greater than or equal than y of n is 1/2. We use mathematical induction to prove that, given the probability of xk being at least yk equals 1/2, the same is true for xk plus 1 and yk plus 1. When adding 1 coin to each player, there are 4 possible scenarios with equal probability. Each player either gets 1 additional head or doesn't. The probability of xk greater than or equal than yk and xk plus 1 greater than or equal than yk plus 1 are both 1/2 given our assumption. Since we deal with positive integers, xk plus 1 greater than or equal than yk implies xk strictly greater than yk. Let's think back to what x and y represent. They count number of heads in the respective flips. Due to symmetry, we can replace the heads with tails and exchange them in the above probability. If we write the number of tails obtained as the total number of coins for each player minus the number of heads, we get that the probability of xk being less than or equal to yk is the same as the probability that yk is less than or equal to xk plus 1. We replace this last element in the initial equation. Knowing that the probability sets xk greater than yk and xk less than or equal than yk are complementary, their sum of probabilities is 1, resulting in the final probability being 1/2, as we wanted to prove. Getting back to the initial strict inequality, we only have to find the probability that x20 equals y20. We use the same trick, switching heads for tails, but only for x. xt20 is 20 minus x20. So, the probability that x20 equals y20 is the probability that x20 plus y20 equals 20. So, we have 20 coin flips, followed by another 21. x20 plus y20 represents the total number of heads in the 41 tosses. So, there are 41 choose 20 possible outcomes from a total of 2 to the power of 41. Thus, we obtain our final answer, 1 over 2 minus 41 choose 21, divided by 2 to the power of 41, or roughly 0.37761. To get to this number, you can use Stirling approximation for n factorial, which is the square root of 2 pi n times n divided by e to the power of n. The previous solution relies on some neat logic tricks to arrive at the result without much computation. But if you do not get to this idea quickly, there always is the straightforward probabilistic approach. x20 and y20 follow a binomial distribution with p equals 0.5 and n equals 20 and 21 respectively. We can then write the probabilities that x and y take a particular value k. We look at the random variable z given by y20 minus x20. Z takes values between minus 20 and 21. The probability we want to compute is that z is less than 0. The probability that z equals a particular value z is the convolution of x and y. So, sum over all values k between 0 and 21 minus z of probability that y20 equals k plus z times the probability that x20 equals k. Replacing 21 minus z with r and applying van der Mon's identity, we get a simplified formula for the probability of z equals z. Now, we sum over all possible negative values to get the probability that z is less than 0, denoting by s the partial sum of combinations, and using the symmetry property, we get an alternative formula for this s. Now, we use the binomial formula for the sum of combinations and plug both values of s in it. Finally, we get the last value, resulting in z less than 0, having the same probability as the one we obtained from the previous solution. As always, you can also check your results by simulating them and seeing that the results hold true. Thanks for watching! If you enjoyed this and would love to see more, like this video, subscribe to the channel and hit the alarm bell to be notified when new videos are released. Leave any comments about this problem below or on the problems dedicated webpage. For more info, please check the description box below. See you next time!